Okay, this is exam 1 from spring 19. The first thing here is I want to know what is the electric field, the direction and the magnitude of the electric field at point A. And the first thing I want to do is just draw the vectors. So I have two vectors. One, I imagine that there's a positive charge there, and then I imagine what is the direction of the force that that charge would feel. Well, it would feel a direction up in a force up in that direction. So my electric field E2 is up and in that direction, and then it would also feel a force in this direction, so that's going to be E1. And by the way, I can go ahead and figure out the angle here, because I know that this angle is 53 degrees, and I know that angle because, well, this is a 3, 4, 5 triangle, so this is 3 and this is 4, and the inverse tan of opposite over adjacent, that's 4 over 3, that's equal to 53 degrees. So I need to know that angle here in just a moment. Then I also need to figure out what is E1 and E2. Well, E1 is going to be KQ1 over R squared. And look, I made the numbers really easy, 9 times 10 to the 9th. Q1 was 9 times 10 to the minus 9 coulombs, divided by this distance squared, so 3 squared, cancels, 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 and just leaves 9 newtons per coulomb. And then in a similar way, E2 is also pretty easy. 9 times 10 to the 9th. Q2 is 25 times 10 to the minus 9, divided by the distance, 5 meters squared, and so that cancels there, that cancels with that, and it leaves similarly 9 newtons per coulomb. So I have both of those vectors are 9 newtons per coulomb. Now I need to resolve the vectors, so I have E1, let's change my color here. That was, yeah, E1, 9 newtons per coulomb is right there. And then I have the x and y components of E2. So it's going to be 9 sine of 53 and 9 cosine of 53. And let's see, what are those equal to? Those are equal to 5.4, keeping 2 sig figs, and 7.2 newtons per coulomb. Now I combine those two x components, and I get 9 minus 5.4. That's going to be a vector that is 3.6 newtons per coulomb in that direction, and then 7.2 in this direction. And what I want to know is what is the magnitude of that vector, and then what is this angle theta, and that'll be my answer. So to find the magnitude, I'll call this just E. E is equal to the square root of 7.2 squared plus 3.6 squared, and then that's equal to 8 newtons per coulomb. And then the angle, theta, is going to be the inverse tan of 7.2 over 3.6, and that's going to be equal to 63 degrees above the positive x-axis. Those are the answers for that question. I understand that question is a little bit harder than these others, but let's see, if you got that question right, what force does the charge experience? Well, if I put a force right here, then, or if I put a charge right there, to find the force, if I know the electric field, is just Q times E. So 3.0 coulombs times 8.0 newtons per coulomb, and that's 24 newtons. And if I want to know the potential at point A, I sum up the individual potentials. So the total potential is equal to V1 plus V2. That's KQ over R plus KQ over R. Right, this is KQ over R. V1 is 9 times 10 to the 9th. That's K. Q is 9 times 10 to the negative 9 divided by R, which is this value for Q1, so that's 3, plus 9 times 10 to the 9th, times negative 25 times 10 to the minus 9 divided by the distance, which is this distance, 5, and that gives me That cancels there. That leaves 3, so it's 27 minus, it's at minus 45, which is, I think, 18. Yeah, minus 18 volts. If you didn't get this negative sign right here, that's a kind of important part when you're doing voltages or potentials, because it's a scalar quantity. If you got everything else right but no negative sign, then that's just half credit. All right, a proton moves from a potential of 8 volts to a place where the potential is minus 2 volts. So if I'm thinking about a mountain here, right, up here I have 8 volts, and down here I have minus 2 volts, and that proton is moving in that direction. That's what protons do, they roll downhill. Unlike electrons, which roll uphill, as we know. And it experiences a potential difference equal to 10 volts. And I want to know, what is the speed of the proton? Well, I know that the work done by the electric field in that change of potential is equal to Q delta V, and that this all goes into kinetic energy. And so this is what I'm working with right here. So I say Q, which is 1.6 times 10 to the minus 19 coulombs, that's for a proton. Delta V is 10 volts, is equal to 1/2 m, what is it for a proton? 1.67 times 10 to the minus 27 kilograms times V squared. And if I solve that for V, which is going to be the square root of 2Q delta V over M, this is a Q right here, then that's going to be equal to 44,000 meters per second. And that's the answer for that one. Now let's go to the multiple choice part. First of all, it's A or whatever one you had. What is the magnitude of the force between Q1 and Q2? So it's 3, 4, 5 triangle. So this is 5 meters. F is equal to K Q over R squared. I made the numbers kind of easy, so they just work out nicely. Because you notice I have 10 to the minus 5 and 10 to the minus 4. That'll cancel out that 10 to the minus 9. Divided by the distance, which is 5 squared. Cancels with that, and that. It leaves me 9 times 2, or 18 newtons. Charge Q is a distance d from charge negative 2Q, and it is twice that distance from charge minus 4Q. Which of these vectors best represents the force on Q? Alright, so what we first need to recognize is that F is equal to K Q over R squared. And so I have two forces here, and then I have two charges here. Hold on, I need to pause for just a second, I'm sorry. So these two forces, or these two charges, exhibit a force F. But notice over here that this charge is twice this charge. So I'm going to put a factor of 2 in this equation, because that charge is twice what it was originally. But also notice that it's twice as far away. So I'm going to put another factor of 2 right there. So what I get is a force between Q and minus 4Q that is half the force between the Q and minus 2Q. So if I draw the force on this between these two, it'll look like that. But if I draw the force between these two, it's going to look like that. And so the answer is neither A nor E. It's either B, C, or D. And the vector that's correct is D. That's number 3. Consider this configuration of charges. Is it possible to place either charge at one of the marked locations and have it experience 0 force? What location? See, that wording's a little strange. I'm going to change it to, is it possible to place a charge at one of the marked locations? It turns out that it doesn't depend on the sign of the charge, so E is not the answer, but we can try it with different charges. Let's just start trying. So I'm going to put a positive charge. It'll have a really big attractive force to that plus 4Q, and then or minus 4Q, and then a slightly repulsive force against those two. Okay, it's really close to this big charge though, so that's going to dominate the force. And B, if I put a positive charge here, it's going to have a really big attractive force to that minus 4Q, and then repulsive forces there and there. So B is definitely not an option, that you cannot get any zero force there. It turns out that A is not either, because this force right here is so much bigger than these two forces, because we're just so close to that big charge. Likewise here, I'm repelled from that one, from this charge. From this charge, I'm repelled, so that's a net force of 0, and then I'm attracted to that minus 4Q. So C will not have a net force of 0. But let's look at D, and it turns out that D will be the answer. That I'm repelled from the two positive charges, and then I'm far away from the minus 4Q, so I have a smaller force, but it's enough force to counterbalance these two forces. So that means that D is the right answer. And if you go through and try a negative charge, you'll find the same reasoning on that. So this configuration of 4 charges. What is the direction of the electric field at point A? All right, point A, due to this charge, the electric field is in that direction. Due to this charge, it's in that direction. And then similar with the other two. They look like that, so the E field is 0. What is the charge of Q2? Q1 has a magnitude of 10 coulombs. It's actually negative 10 because the field lines go in, so I can get rid of C. And I know that Q2 is going to have a bigger charge, so I can get rid of that, and that just leaves B. But let's just see how we do this. Look, I can think about the field lines being proportional to a certain amount of charge, and they're going to be proportional to 10 over 3. That is that each field line will be proportional to 3.3 coulombs. Okay, you can do this in a different way too. You could set up a ratio. I think this is probably the easiest. So if each of these is 3.3, over here I have 5 field lines, so 5 times 3.3, that's that 17. And it is negative because the field lines end there. Electric field is always a measure of force per unit charge. You move a charged insulating rod towards 2 equal-sized neutral spheres. One is conducting and the other is insulating. Which would you expect to become more strongly polarized? The conductor would. The insulator could become polarized, but the conductor will get a bigger separation of charges. You have 3 neutral conducting spheres and a charging device that allows you to place Q on any neutral object. You want 2/3 Q. All right, so I have 3 here. What I do is I put Q on this one and then Q on this one. And then I touch all 3 together. See, because if I have 2/3 Q, if I have 3 spheres with 2/3 Q, that means that I have a total of 2Q. And so I have these 2Q, and then I just separate it between the 3 spheres by touching them all to one another at the same time. So A is the right answer. 2 charged balls are repelling. What can you say about their charge? One is positive, or one is negative, or either both are positive or both are negative. So D is the right answer. Magnitude of the charge on an electron is 1.6 times 10 to the minus 19. If I bring this rod up to these, I get this one a negative and this is positive. So L is negative, M is positive. Capacitor consists of 2 metal plates. What is the capacitance? So C is kappa, epsilon naught, A over D. That's 1.8. 8.85 times 10 to the minus 12. That's on your equation sheet. A is 0.3 and D is 1 micron. And that works out to be 4.8 times 10 to the minus 6 farads, or 4.8 microfarads. Capacitance of a parallel plate capacitor can be increased by doing what? All right, well, C is equal to epsilon naught A over D, or kappa epsilon naught A over D. Increasing the charge doesn't do anything to the capacitance, nor decreasing. If you increase, if D goes up, that means C goes down, so it's not 3. If D goes down, that means C goes up, so 4 is 1. And if you decrease the plate area, that decreases the capacitance, so only 4. Parallel plate capacitor has a potential difference of 10 volts and then is disconnected from the charging battery. That means it has a constant Q. So Q is equal to C times V. This is constant. But then I double the plates of the area of the plates. So if I double the plates of the area, that means I double the capacitance. So if that goes up by a factor of 2, this has to go down by a factor of 2. Whereas it was 10 volts, now it's 5 volts. So in that way I can get a variable voltage supply just by changing the dimensions of the capacitor, changing how close the plates are or how big the plates are. If I have an electron at point B, if I have an electron right here, it's going to move towards A. So 16 is A. Proton moves from point A to point B. Let's go back and look at that. If a proton moves from point A to point B, that is a delta V of 2 volts. It's actually negative 2 volts, but we're just looking at the magnitude here. So our change in voltage is 2 volts, and our energy that it gains is equal to Q times delta V. All right, let's do potential energy here. And that's going to be 1.6 times 10 to the minus 19 coulombs. That's for a proton times 2, which is going to be A. If the distance between equal potential lines A and B is 4 microns to the far right, what is the electric field at this point? All right, let's go back and look at that. So here, notice the electric field is greatest over here, where the equal potential lines are close together. Over here, where they're spread or farther apart, the electric field is less. So big electric field over here. By the way, you biology folks, this is important, especially in the neurons, when you have this electric potential that's propagating along, gosh, what's it called? The axon, I think, when it's propagating along that neuron. There's an electric field that is between the cell membrane, the inside and outside of the cell. Anyway, where was I? Between A and B, that is a delta V of 2 volts, and the distance between those two is 4 microns, and I want to know what is the electric field. This is where knowing the units of the electric field is kind of important, because the units of the electric field are newtons per coulomb, but they can also be volts per meter, and that means that electric field is equal to my potential divided by my delta x, just looking at the units. And so if I want to know the electric field, it's just going to be 2 volts divided by 4 microns, and that's going to be 5 times 10 to the 5th. That's 2 divided by 4 times 10 to the minus 6, just 5 times 10 to the 5th. Okay, this one seems simple, number 19, but you really have to think about it a little bit. The answer is going to be B. Let me show you why. First of all, we know that V is equal to KQ over R, and at point B, it is situated such that KQ over R for the two charges is equal but opposite, because one's positive and one's negative. So let's imagine that the potential at point B due to this charge is V. And then over here, I have 3 times the charge of what I had, right? 6 is 3 times 2. But look, this distance is right there, but then I have 1, 2, I have 3 times the distance to the 6Q charge. And so these two numbers cancel out, and so they both have a potential V, but that's opposite. So the answer is B. And that's not true for any of the other places that either, my positive or my negative dominates based on my location. And now 20. How is electric potential related to electric potential energy? Potential is an energy per unit charge. Yeah, all these others are wrong. Okay, so that's it. You might see a little bit different order. I'm going to rearrange the questions so that they are so that you can see all those that are related to one another, but otherwise it'll be the same.